In this screencast, we're going to talk about atomic mass units, we're going to talk about isotopes, and then we're going to talk about how to calculate the average atomic mass. The masses of nuclear particles are too small to discuss with standard mass units, grams. So the atomic mass unit was established to express relative masses of atoms and subatomic particles. So atomic mass units a lot of times are abbreviated as AMU. If there was a little jump there, you didn't miss anything. I had to pause it and then restart it. So I wanted to give us a definition for atomic mass units. This is just the unit used to express the relative masses of atoms and subatomic particles. This is equal to 1/12 of a carbon atom. And a carbon atom has 6 protons plus 6 neutrons. And so that ends up as 12 AMU. In some older text, you're going to see 1 AMU described as 1 Dalton, which a lot of times is shown as DA. And that's, of course, named for the English chemist John Dalton. So we talked about all the different components of the nuclear atom in the last screencast, but I wanted to review really quick and point out some abbreviations. The electron is a lot of times abbreviated as E-, and it has a -1 charge. And when we look at the masses, well, let me talk about masses in a second. Proton is a lot of times abbreviated as P+ with a +1 charge, and neutron is with an N with a 0 charge. Now, let's look at masses. These are the actual masses of the electron and proton, and they're a little unwieldy because we are dealing with very big and very small numbers. However, when we look at them as far as AMUs, they become much easier for us to deal with. If we see here, we generally consider a proton as 1, we generally consider a neutron as 1, and then if we look here, electrons have a mass that's about 1/2000 smaller than the proton or the neutron. So it's very small in comparison to these two. So these are the masses within the AMUs. Now, there's a couple different ways that we can symbolize the number of protons, neutrons, and electrons in an atom. If there's a little bit of jump there, I didn't like the way that lecture went, and so I went back to re-record it. So we are talking here about isotope symbols or nuclide symbols. Isotope, nuclide sometimes are used interchangeably. And what we're going to notice here is there are different ways for us to represent the number of protons, electrons, and neutrons on paper that are in an element. And one way is using this symbol where you have the elemental symbol here and then you have 2 numbers here. The top number that you're going to be given is the mass number. This is the total number of protons and neutrons in the nucleus. It's really important for you to know that this has to be given to you, right? And what I mean by that is you can't find it on the periodic table. Okay. Then the X there, that's going to be the element symbol. This you do find on the periodic table. And it's going to be 1 or 2 letters, and you need to keep the same capitalization. For example, if you're talking about cobalt, it's CO, not CO. This tells me it's cobalt. This looks like carbon monoxide. So you need to make sure you keep the same type of uppercase and lowercase on the periodic table. And you'll be given a periodic table with your exam. Then the bottom number is going to be the atomic number. And this is the number of protons in the nucleus. Okay. And you can find that on the periodic table. It's generally it's always going to be a whole number, right? The atomic number is always going to be a whole number. It's generally at the top. And so you can see here for gold, it's 79. For silver, it's 47. So you find this, it can either be given to you, but you can also find it on the periodic table. And it's going to be the whole number. Okay. You can also sometimes see a symbol where you have the element like this, the name written out. So for example, let's say you want to do silver, right? And you want there to be, right? Then you'll have a number written after it, like 110. That is the mass number. And the idea here is the mass number has to be given. That's why it's written after. You can always look at the periodic table and find the atomic number. And so that's why we see it that way. So let's look at some examples. So here are two examples. This is uranium. And if you look at the periodic table, you're going to see that uranium has a atomic number of 92. And so both of these are uranium. That's the number of protons. The number of protons defines what the element is. Okay, so the number of protons and what I mean by that is every uranium is going to have an atomic number of 92 and 92 protons. That's how it goes. But one of the things that we're going to see here is that this atom of uranium and this atom of uranium have different numbers of neutrons. Now we can figure out the number of neutrons by taking the mass number, which is the number of neutrons and protons, and subtracting the number of protons, or the atomic number, okay? And so when we do this, we see that uranium-235 has 143 neutrons, and then uranium-238 has 146 neutrons. There's a relationship to describe these two atoms. They're called isotopes, and these are atoms that have the same atomic number but different mass numbers. Another way to say this is these are two atoms that have different numbers of neutrons, right? And so these are isotopes. Now, let's look at an example that you would have to solve for, in class or in your homework. And it says, how many protons, neutrons, and electrons are present in a single atom of the following? Now, you're going to need a periodic table for this. It's just going to make it, I can't do it without a periodic table, so you need that. And so I am going to draw the information that you need from the periodic table. There's bromine. And then I'm going to draw here the information you need from the periodic table, which is iron. Okay. Now, protons are positive. Okay. And we can get this from the atomic number on the periodic table. Neutrons are neutral. We are going to figure out our neutrons, we are going to have to take the mass number and subtract the protons. Now, when we talk about electrons, electrons have a negative charge, and atoms can lose or gain electrons, okay? If there is no charge, the number of protons equals the number of electrons. Now, what do I mean by no charge? When we look at bromine as it's written there, okay, that would be just bromine 79. There is no negative or positive charges above it. And so what I mean by that is if you look at bromine here, there's nothing negative or positive around it. If bromine has a negative charge like that, then we have to mess around with electron numbers. We're not there yet. We're going to talk about that when we get to ions, but I wanted you to see the difference. So here we go. Bromine 79. We go to our friendly periodic table and we say, let's find the atomic number. We know that's going to be the whole number. And that means my protons equal 35. Then I'm going to say, okay, this guy doesn't have a charge. There's no negative or positive or any sort of superscript here. And so I can say, great. My electrons then equal the number of protons. So it's 35. So now I have to find my neutrons. And this is where I have to do a little bit of math. I take my mass number, which is 79, and subtract my number of protons, and that gives me 44, which is my number of neutrons. Okay. Now, we can go down here to bromine 81 and do that again, where we look at the atomic number on the periodic table. We say, look, our protons are 35. There's no charge, so our electrons are also 35. And then when I come over here to the neutrons, I'm going to have 81 minus 35, and that gives me 46. Bromine 79 and bromine 81 are isotopes, right? Because they have the same number of protons, but a different number of neutrons, okay? Now, we're also going to do iron 56. If you want to pause and try this on your own, you're more than welcome to, and then check your answer. When we look at iron on the periodic table, we see the atomic number as 26. So my number of protons are going to be 26. There's no charge, so my number of electrons are also going to equal 26. And then to figure out my number of neutrons, right, I'm going to take 56 and subtract 26, and that gives me 30. And that's my number of neutrons. So we'll do more of these in class. And of course, you can also come to me if you have any questions. Now, let's talk about average atomic mass. Individual atoms of a given element have a specific mass, but a macroscopic sample of the element will exhibit an average mass that depends on the mass of each isotope, right? Because you've got some atoms out there, like when you look at bromine, you've got some that, you know, have a mass of 79, but you have others that have a mass of 81. Well, we can't really get down there and separate all those out. And so instead we use something called a average atomic mass that takes into account the masses of all the isotopes of an element. And so the average atomic mass is just a weighted average of masses of all the isotopes of an element. And we're going to see how to calculate that in just a second. Now, when we start to talk about calculating it, though, I'm going to refer to natural abundance, or you'll hear natural abundance. And the natural abundance of an isotope, right, is the proportion of that particular isotope in a natural sample. So for example, if bromine 81, if there's just a little bit out there, maybe like 1%, it's not going to affect the average atomic mass as much as if it were like 90%. And so those percentages that we talk about are the natural abundance. So let's look at how we calculate an average atomic mass. We are going to look at this problem. We're going to calculate the average atomic mass of chlorine if 75.77% of chlorine atoms are chlorine 35 and 24.23% are chlorine 37. When you look at this and we look at kind of things that are important, for the time being in chemistry, numbers are really going to be important. And so the 75.77 goes with the chlorine 35 and the 24.23 goes with the chlorine 37. And those are the numbers that we're going to deal with. Now, the first step to solving this is that you need to convert the percent to a decimal. The way that you do that is you need to divide by 100. So for the chlorine 35, what you're going to do is you're going to take the 75.77% and divide by 100%, and that's going to give you 0.7577, and that's the abundance there of chlorine 35. Then we're going to look at chlorine 37, and what you're going to do there is you're going to take 24.23%, you're going to divide it by 100%, and that's going to give you 0.2423 chlorine 37. Okay, so that's your first step. You're going to convert the percents to decimals. Then your second step is that you're going to multiply the percent Nope, I said percent, and I definitely was thinking decimal. So let's go back, multiply the decimal by the mass of the isotope. So what we're going to do here is we're going to go 0.7577 times 35. I'm going to go ahead and make this 35.0 AMU. The 35.0 AMU comes from this number. If you don't have that, it will also be given to you. And I've got a different example. I've got another example to show you that. Then, and so we're going to do that math. That gives us 26.5 AMU. Then we're going to come here and we're going to take, for the chlorine 37, the 0.2423, the decimal. We're going to multiply it by the AMUs that are given with the number, so 37. And that gives us 8.97 AMU. Then the final step is you need to add the masses. So when you do this, you take 26.5 AMU and you add 8.97 AMU. Now you're adding, so you do have to use your addition significant figure rules, and that's going to give you 35.47 AMU. We're going to look right here to see where we need to round, and that's over 5. So that's going to give us 35.5 AMU. Now, I love these problems because there is a really great double check. You need to double check that this mass that you get is between the masses that are in the problem. So this needs to be between 35 and 37, okay? This problem is saying look, we've got 2 isotopes of chlorine. We've got chlorine 35 and we've got chlorine 37. And that's it. Those are the only 2 in this sample. That means it would be really weird if all of a sudden you got, a mass of 97. That would give you an idea that something's off. If you got a mass lower than 1, right, that would give you an idea that something's off. If it's negative, something's wrong. So these are great double checks, but this needs to be between the isotopes that you're given. So for example, let's look at this one. Okay, it says the following table contains the atomic masses and relative abundance of isotopes of neon. What's the average atomic mass of neon in the sample? Okay, these are my individual masses that I'm given. I see that it's 19.9924, 20.9940, 21.9914. I know my answer has to be between the smallest number there, 19.9924, and 21.9914. So it has to be between both of those before I even start this problem. Okay. So let's follow the same steps that we did on the previous problem. The first thing we're going to do is we're going to convert the percent to a decimal. So when we look at this for neon 20, that's going to be 90.4838%. We divide by 100%, and that gives us 0.904838. Then for neon 21, we say great, that's 20.9940. We divide that by 100%, and that gives us, nope, I looked at the wrong number. We're going to come here and we're going to do 0.2696%. We're going to divide by 100%, and that gives us 0.26 0.002696. Sorry, I was looking at the wrong place in my notes. Then we're going to come here and we're going to go to neon 22. And we're going to see it's 9.2465%. We're going to divide that by 100%. When we do that, we get 0.09245 as our decimal. Okay, so that's the first step. The second step is we need to multiply the decimal by the mass of the isotope. So when we come here and do that, that's going to be, we're going to go back and look at the number that's circled in the middle of the column. So for neon 20, that's going to be 19.9924 AMU times 0.904838. Then we are going to do neon 21, which is 20.9940 AMU times 0.002696. And then we're going to do neon 22, which is 21.9914 AMU times 0.092465. Now I want you to know, I go ahead and write everything down in this problem because then I just have to pick up my calculator one time. So when you do this math, you're going to get a lot of numbers, and when you do it, you need to, so that you don't spend a lot of time writing a bazillion numbers, you want to match it to the number of decimal places in the AMU here. So when I do that, I get 18.0898. Here I get 0.0565, and here I get 2.0334. And then step 3 is going to be, and I'm going to do this in a different color, it's going to be to add them. And instead of writing them again, I'm just going to do like this. And we're going to add them together. That's going to be 20.1797 AMU. Let's make sure that we have units on our numbers. There we go. And so that's our final answer. And so we're going to go back and double check, and we see that 20.1797 are between the lowest and the highest mass numbers that were given. And so this makes sense. Now, the other thing that makes sense is that I want you to notice that this is 20.1797 is closest to 19.99. And the reason for that is 90% of the abundance is this isotope. So we would expect this number to be closer to this isotope. It's kind of like if you think about your grades. Your grades are a weighted average, just like this is. And a bigger portion of your grade comes from exams. And so you would expect your final grade to be very close to that exam grade. Okay. All right. Well, this ends the screencast. If you have any questions, please feel free to pop by my office and ask.